All right. Good morning. How we doing? Put the camera right here. Look at all these shining faces. All this energy. Okay. I'll have to meet your energy level right now. Okay. With all my enthusiasm anyway. How are we doing? Some vocalization's fine. Thank you. I'll take it. All right. So last time we were covering some Lagrangian mechanics, which is fun. It can get a little bit mathy on the board, but on Thursday, we should be doing some MATLAB Symbolic Toolbox to help us out with that, but we'll get to that in a second. Your homework number 3, we should have up today, okay? It's going to cover things like trajectory optimization up through direct collocation, because we now have done examples of single shooting, multiple shooting, direct collocation, all three, the big 3 trajectory optimization methods, okay? And I can't even tell you how cool it was, at least for me. We set up a pendulum and said, hey, you have limits on the amount of torque on this pendulum. You got to get up here. How do you do it? And it is really tight limits. You can't like lift your arm too well, right? Ooh, with these tight torque limits. What did it do to solve the problem? Anybody? Swing, you would say. Pump it like a swing and get up to the top. Clever. Clever. It figured it out on its own. You set up the problem in a smart way with direct collocation, and it figured out a cool solution. That's some of the magic of optimal control, right? If you know what you want, and you set up the problem right, you ask the right question to the right optimizer, and it'll just figure out clever things. That's what's cool about it. All right? So that's what's going to be covered on the homework is trajectory optimization, setting up single shooting, multiple shooting, direct collocation. And now what we're moving toward is how we deal with complicated dynamics for these systems, okay? So far, we've been doing pendulums. For your homework, you've done pendulum on a cart, okay? We haven't done anything that has, multiple inputs, multiple outputs, particularly for a mechanical system which has lots of interconnected links, like these multi-bodied systems, okay? Again, talk about a robot arm, you'll have one joint connected to one body, another joint connected to another body, another joint connected to another body, right? And last time, we started talking about Lagrangian mechanics, which would tell you just what the equations of motion are for these things. Because in your mechanical engineering curricula up to this point, unless you're a grad student who's taken advanced dynamics, you probably haven't been exposed to that, okay? And that's what we covered as a tool last time, okay? So, but today, we're going to build upon the Lagrangian mechanics from last time. We're going to fast forward through the rest of the derivation of the pendulum on a cart dynamics that we did at the end of last class, so we can get to the nitty-gritty, because it's a matter of sort of turning the crank on the math to get to where we are here, okay? So let's go. Today we are 2026-03, and what, 31? No. Okay. I'm going to act in disbelief every date. As the inexorable march of time moves forward, I'll be surprised each time. Okay. Yeah, and DJ, could you check the camera, how much time is left on the camera? It's just the backup. It's not a big deal. But all right. So last time, recall Lagrangian mechanics. Four minutes. We don't need it. I think we're good. We're recording here. You can always stop the camera there. All right. All right. So we got this. We'll call Lagrangian mechanics. All right. So this is for multi-body. Great for multi-body dynamical rigid body systems. Okay? So if you have like most mechanisms you would ever like design in a physical system, I mean, even if you have things that aren't rigid like springs, if you can write them as potential energy terms, it fits into Lagrangian mechanics just fine. What you don't want are floppy noodles, you know, these really soft continuum mechanics things. You'll have a hard time setting it up with this formulation. But for so many different devices, you can get the dynamics with Lagrangian mechanics, okay? And what we had set up, so we had a couple things. We had the idea of generalized coordinates. That's just degrees of freedom, okay? Gotta make sure I have things to throw, otherwise, it's always a marker, right? How many degrees of freedom do we have when this marker is in three-dimensional space? You've got 3 translational, 1, 2, 3, 3 rotational, yaw, pitch, roll for this little marker. That would be 6 degrees of freedom. That's different than the number of states, okay? That's the number of generalized coordinates you would need for your system, okay? All right, on top of that, we covered the idea of the Lagrangian, which was defined as being equal to T minus V. What was T? Anyone remember? Kinetic energy, just like from dynamics. Who decided that? Honestly, off the top of my head, I don't know. What did V stand for? Potential energy, right? And your generalized coordinates, we called Q of T. Sometimes you'll see it called theta of T in different textbooks. Bar of T I've seen, called Lagrangian. All right? So this is an energy-based method for computing our dynamics, right? And we had the Euler-Lagrange equation. Okay? And that was partial L, partial Q. Wait, did I get that right? Sorry. d dt, partial L, partial Q dot, minus partial L, partial Q, is equal to your non-conservative forces, okay? So for 0, this is an energetically conservative system. Right? You could also write it as, if you have any external forces, these non-conservative forces, I'm going to write them as tau. We write them as non-conservative, work non-conservative. I'm going to write here that these are non-conservative forces. Okay? So that's if you have a motor, adding energy or moving energy. It could be a motor, could be friction. Those are kind of your classic ones, right? In our example we had, which is a pendulum on a cart, we did not have any friction in our pendulum on a cart last week. So we just said it was equal to what, friends? 0. Quick life hack with any of my lectures and many math lectures. If I ask you what something equals, 90% of the time it's 0. Right? Hey, what does that equal? 0. Okay? Those are your non-conservative forces. Okay? We're going to call this an unconstrained system. Meaning that every single Q is an actual degree of freedom for your system. Okay? There's another cool trick that you can do with Lagrangian mechanics that we'll see if and when we get to an actual lecture proper, but it's so totally doable. This marker, okay, moving around in all sort of 3-dimensional space, has 6 degrees of freedom, right? Okay? Well, let's turn it into a pendulum by attaching it to a pin joint that's just on the ceiling. Okay? We would probably represent that as a single degree of freedom, the angle of the pendulum. That's what we did in our first example last Tuesday, right? That makes sense. That makes our life easy. I like that. We have one actual degree of freedom. It can move this angle, so we have one generalized coordinate, that angle, right? But, my friends, there's another way you could write the dynamics of this marker as a pendulum in Lagrangian mechanics. You could give it all of its degrees of freedom and then say, I'm going to add physical constraints to turn it into a pendulum. In fact, I'm going to make it so this pin right here, like this end here is pinned, so it cannot move, this end cannot move vertically toward you and left and right. Impossible. That's 1, 2, 3 constraints I put on this thing right here. Okay? And this pin prevents it from moving in that direction, right? If it's pinned like this, it can't move like that, right? That's a 4th constraint. And it can't twist when it's in that pin, right? That's a 5th constraint. So you go from 6 degrees of freedom plus 5 constraints, or minus 5 constraints. What's the math on that? And it's not 0. 1 degree of freedom. So you could have 6 generalized coordinates, the x, y, z position of the center of this marker, and all 3 rotational angles of it, and add 5 constraints to make it a single degree of freedom. Okay? You can do that. It's just a slightly different formulation of the Lagrangian mechanics, or the Euler-Lagrange equation. d dt partial L partial Q dot. You'll notice that I'm skipping the of t's for my sanity. Okay? Minus partial L partial Q. This is all the same on the left-hand side. But on the right-hand side, I still have any non-conservative forces, tau, plus J transpose lambda. Okay? Where lambda are your constraint forces. Called your Lagrange multipliers. It's just a fancier way of saying a constraint force in the context of mechanical systems. Okay? We've talked about Lagrange multipliers in the past in terms of optimization constraints, okay? Or we might have, okay? And here, this J, this is called the constraint Jacobian, okay? Where if you have a constraint where you say, hey, I want some function of my coordinates q to be equal to 0, J is the Jacobian of that with respect to q. So it's partial f of q with respect to q. We've done Jacobians before, many a time in this class. So in the case of this pen, I would create a function that says, hey, whatever this position is, it's got to stay at, as a function of whatever all my coordinates are. I create a function that says when the constraint is satisfied that this is a pin, this equals 0. This function equals 0. So if you take J, which is a matrix, it's Jacobian, you transpose it, multiply it by the Lagrange multiplier normal force, your constraint force. I'll give you another example. I have a ramp. You all took physics, right? I'm going to roll. This is a block, not a rolling marker. This is a block. Do you believe me? I'm glad you believe me. I've gaslit you all. Okay. All right. I let it roll. Okay. This ground is a constraint. Until it rolls off, ignore when it rolls off. You could treat this ground as a constraint where you can't move through the ground. The position of this block, it must stay on this ramp at all times, right? That's a constraint on the position. Now, when you do that calculation, when you're trying to derive the equations of motion of a block on a ramp, what's one of the forces that you have to compute? What are the forces on this very much not a marker, it's a block? What are the forces on it? Come on. Gravity and normal force, exactly. That normal force, it's a constraint force. It prevents the block from going through the floor. So you have to solve for it, right? That normal force in order to get your equations of motion. That's what lambda is. All your years in physics, you've been calling it n for normal force. That's fine. It is, in fact, normal to the ground, perpendicular. That's correct. But a generalization of that is lambda, a constraint force. Okay? And you can apply that to all kinds of constraints. Okay? Pin joint constraints, sliding constraints. The only thing that gets tricky is that this constraint, you'll notice it is dependent upon Q, your generalized coordinate, your positions, right? What is not in this function here? Q dot. What are Q dots? Speeds. What's that? Velocities, yeah. Velocities. This is not a constraint. This works well with constraints that are only dependent upon positions, not velocities. Has anyone ever seen a children's toy where there's like a metal long thick wire and there's a bead that rolls along it, a bead on a wire? That's a constraint based on position. That bead can only be at certain positions. All right. The ramp, it can only be on certain positions on the ramp. You can't be up here. You can't be down here. You're on the ramp. The pin joint can only be here. This is a position-based constraint. This is a cool name. Does anyone know what the cool name is for a position-based constraint? I'm probably teaching you new stuff here, so that's totally cool. It is called holonomic constraint. This form works great for holonomic constraints. If you have a velocity in your constraint, it is no longer holonomic. That's trickier to deal with, and we're not going to cover in the near future. Take a more of an advanced dynamics class. There are ways to do it, but it won't work as well in this formulation. Okay? Can anyone give me an example? I gave you lots of examples of position-based constraints. Anyone think of a non-position-based constraint? Yeah. A motor with a max speed. That's a good one. I didn't think of that one. Okay? That is, yeah, that's correct. Didn't think of that one. Anyone watch the Olympics, the Winter Olympics this year? Nobody? Nobody? Yes, some people? Anyone know, start listing events in the Olympics. Anybody? Winter Olympics. Curling? Hockey? Hockey. What do the hockey players locomote on? What's on their feet? Skates. Interesting. Interesting. Skates. Skates. Skate on the ground. Can move forward and backward, right? Can it move sideways very easily? It can't. One might consider that a strain on its velocity. It can go in the direction it's pointing. It can't go side to side. So skates are a classic example of non-holonomic constraints. Okay? So non-holonomic constraint examples. Skates. We have velocity constraints, direction constraints. Anyone drive here this morning? When you saw, oh my goodness, I want to parallel park. Oh great, I'll just go up to next to go up next to the parking spot and I'll go, yeah, I'm in. Did anyone do that? I hope not. You have a very fancy car if you could. You can't, right? Because the wheels, you could only roll in the direction of the wheels. You can't slide the wheels to the side, but not without extreme effort. You can effectively call that a velocity constraint, right? So wheel turning driving. Okay? So Gesundheit. So when there are ways to handle this. You know, we know how to do non-holonomic constraints, but they won't fit in this form as nicely that we have here. Isn't that neat? So it might be something you can do for fun is write out the equations of motion for a pendulum in the plane, so you have 3 degrees of freedom, up, down, left, right, 1 rotation. Pin it with a holonomic constraint and see if you get the equations of motion. Okay. So there we have our Lagrangian mechanics for a couple of different instantiations. One is no energy being created or destroyed. It's conservative. Right-hand side is 0. You have stuff that's going to change the energy, some torques right there. And I will say it's a vector where T1, T2, up to Tn, these are torques on each forces, generalized forces or torques on each Q. So if your first Q for this pen is a force, is let's just say the sideways position, okay? A force that pushes sideways would be the first of these forces, okay? Yes, I called it a tau, but if it was an angle, it would be a torque. If it's translational, it'll be a force. Just think of it as a generalized force. Doesn't matter if it's a linear force or a rotational torque. Okay? All right. So let's go back to our example, or a very similar example to what we covered last class. Okay? We have some pendulum on a cart. We have some mass 1 and some mass 2. A little different than the one last class. This is the one exactly from your homework, okay, where there is a center of mass there. This is a little sloppier than I wanted. We're going to redo this ever so slightly. Center of mass in the middle of that. This is from homework 1. Mass 1. Got gravity. Okay. The pendulum on a cart. And cart. Some people call that the cart pole. We did a whole bunch of math, and we were working through all of the Lagrangians. We're saying, hey, what was all your T's? What was all your V's? We were setting that up. We were doing tons of partial derivatives. Okay? The only difference between what we're doing now and what you're doing in your homework is that the center of mass here is at the center of this rod as opposed to at the end of the rod like a bob at the end. Only difference. So it's going to create some minor changes in the inertias, and that's it. Okay? And if you solve out all the equations of motion, this is what you get. Okay? M1 plus M2 S double dot of t, where S we'll call the position, S of t the position of the cart, and here's your angle, theta of t. All right? Minus 1/2 m2 L theta dot of t sine of theta of t plus 1/2 m2 L theta double dot of t cosine of theta of t equals 0. And then your second equation, which will be 1/4 m2 L squared theta double dot of t plus 1/2 m2 L s double dot of t s double dot of s double dot of t cosine of theta of t plus 1/2 m2 g L sine theta of t equals 0. Okay. It'll all simplify down pretty nicely. Look, it could be, trust me, it could be a lot worse. I was telling you, some of our robots, if you printed them out on normal paper, this would cover football fields, okay? That's why we don't do it by hand for these incredibly complicated systems, okay? So you have these equations. You'll notice that right now we have no forces on our cart, no non-conservative forces. So we have no friction. We have no external motor acting on it right now. We'll keep it that way for the moment, okay? But this is a little bit of a sloppy way to write equations, when sometimes we have a really compact way to write them as matrix multiplications. As we covered this at the end of our second lecture, we called it the manipulator form. Okay? Where you have some inertial matrix M of Q, Q double dot, I'm getting rid of the of t's for my sanity, plus some C of Q, Q dot, plus some G of Q is equal to 0. On the right-hand side, you can add all of your external forces or torques you want, and you can add any polynomial constraints that you want on the right-hand side for all the variations we put earlier, okay? But look how lovely and clean this is. Oh, how nice. And it groups up all the terms of your physical system in ways that you can kind of understand from first principles. This right here, this is your inertia. Your inertial matrix contains all the information about your masses, your rotational inertias, okay? So again, if we're talking ice skating, let's talk figure skating. We've all heard the example of figure skating where, like, oh, when you're spinning, you put your arms out wide, you get your large moment of inertia, you spin slow. You pull in your arms, you spin fast, right? Okay? Now, that inertia changed based upon what? The positions of my generalized coordinates, in this case, my arm angles, okay? It's only dependent upon positions. It's not dependent upon velocity. Inertia is never dependent upon velocity, right? And we see that here. Your inertia is only dependent upon what? Q, positions. And you multiply it by what? What's Q double dot? Accelerations. Oh my God. Oh my gosh. Mass times acceleration. This is good old physics 1, F equals ma, written fancily, to use the technical term. Here, this is your gravitational component. Okay? The force of gravity on your system. If I have my arm up here, straight up, it's not going to cause an acceleration on my arm, straight up, but it's going to have more of a torque on my arm if it's over here, right? Gravitational forces are going to affect it differently. The accelerations. Again, is that dependent upon speed? No, it's only dependent upon position. Where are all these speed and velocity dependent terms? They're here. This is called your inertia. Inertial matrix. Okay. This is our gravitational term, the vector. And these are our Coriolis terms. Coriolis terms. Also a vector. Okay. Now, Coriolis terms are definitely dependent upon speed. They all get grouped up in there, right? Okay. So this is a way, so you can take these equations here, and you can literally pick out which one of them are inertial, Coriolis, or gravitational terms. Can we do that? Just from what we know. If it's multiplied by an acceleration, it's what kind of term, friends? Inertial. Okay. Hey, look, acceleration. Inertial. Acceleration, all this stuff, inertial. Hey, double dot, acceleration, inertial. Double dot, acceleration, inertial. Okay? So you could rewrite m of q dot, m of q, q double dot, just that one term only. We could rewrite this as the matrix multiplication of all of the terms, and then over here we have our accelerations, s double dot and theta double dot of t in a vector. I'm just regretting bounding my matrix first. Here's what I'm going to do. Can I write this? Yes, I can do it. I think I can fit it. This is m1 plus m2. Where is that? Up there, right? m1 plus m2 times what? S double dot. It's in the first equation. This goes in the first row. It's multiplied by s double dot, so it's the first column. Now let's find theta double dots. It is right there. So it's going to be in the first, it's in the first equation. It's multiplied by theta double dot, so it's going to be 1/2 m2L cosine of theta of t. Cosine of theta. Okay? And second equation, it's the second row. That's 1/4 ml squared times theta double dot. Perfect. So it's 1/4 ml squared. Nice. Oh, sorry, no. That's times theta double dot. That's the second one, right? So that's got to be over here. Sorry, move that to the side. 1/4 ml squared. And just finished it out, this one will be 1/2 m2L cosine of theta. 1/2 m2L cosine of theta. All right. Hey, that's m of q. And you can check, is it actually dependent upon only q and not q dot? Well, I don't see any theta dots or s dots in here, do you? That's good. Doesn't mean we did it right, but it's a good indicator, right? Times this, because q was equal, q of t, our positions are s of t and theta of t, right? So q double dot is s double dot of t, theta double dot of t. Gives us our m, right? We managed to find all the terms that are inertial terms. We did it by hand by looking at the equations. Using a symbolic toolbox, if we're just looking for the Jacobians of particular terms, We've done this many a time. You take the Jacobian, and it gives it to you. Inertial matrix, always square. Always square. Always a square matrix. Also, a pattern you will see in many of your inertial matrices, when you're looking at your inertial matrices, if along the diagonal, and if it kept going, you'd have more along the diagonal of this matrix. This is like the inertia of this body. So if you want to move the entire cart translationally, what's the translational inertia of the entire cart? Oh, m1 plus m2. What's the inertia of theta? Well, it's our rotational inertia, right? ml squared. The only reason it's 1/4 ml squared instead of 1/2 ml squared is because the mass is at the center of the rod. Remember at 1/2 ml squared from physics. That's your moment of inertia. And that just pops out from doing the Lagrangian mechanics and pulling out the inertial terms. Incredible. Okay? Now we were just able to just pick out by hand all of the inertial terms because we're like, hey, look, there's theta double dot, theta double dot, theta double dot, and where's s double dot? There you go. And we could do the same thing and say, hey, what are our Coriolis terms? Well, they're the ones that have q dots in them, right? And you could say, oh, look, there's a q dot there. There's a theta dot there, because there's theta dot. And what else we got, friends? We've got the only one looking around, looking for other dots. There might be only a dot. That'll be our Coriolis term. And then you have all your g terms, which are going to be just dependent upon q. Oh, look, there's one. Yeah, that's it. And you can pull out those terms as well, put them in a vector. Okay. But what I want to instead do, a couple things. One is let's talk about how this is nice. How do we solve for accelerations? Right? If you are, what do we want to use this for? A lot of the time it's simulation, right? We want to know if we apply a certain force to a system, how's it going to accelerate? And we need to know that because the acceleration is going to be the derivative of one of our states, the velocity. And it's the hardest one to get. Okay? Well, imagine we have m of q, q double dot, is equal to a whole bunch of other stuff, c of q, q dot, plus g of q is equal to all of our torques. Let's ditch the constraints for now just to save our sanity. Well, that's a slightly more fun discussion, how we get those Lagrange multipliers. Okay? Well, we could move everything that isn't multiplied by acceleration. So this whole term, keep that on the left-hand side. Q double dot is equal to tau minus c of q, q dot, plus g of q. And this is a matrix. So we can multiply both sides by the inverse on the left. That's basic linear algebra. That's like algebra 2 level linear algebra. Q double dot is equal to m to the minus 1 of q of multiplied by tau minus c q dot plus g of q. That's just me basically dividing by m of q, just with a matrix way, right? Anyone confused by that step? Because we're trying to get this. By making that multiplication step, the inverse of a matrix multiplied by itself is what kind of matrix, friends? You gonna make me rhyme? Identity matrix. Or the matrix that is effectively 1. You multiply it by anything, it's itself. The identity matrix, right? So in effect, you solve for Q. Q double dot is equal to M to the minus 1 of Q. Tau minus C of Q and Q dot plus G of Q. Hey, this equation solves for my accelerations. And when you're solving for accelerations, when you have a bunch of forces, we call that forward dynamics. Okay? We know what our forces and torques are. We ask, what are our accelerations? Turn that into accelerations. If you're simulating a physical system with accelerations, that's what you're doing. You're doing forward dynamics. Well, I don't think you're even calling it forward dynamics. You're probably thinking of calling it dynamics. Well, you took dynamics 1 and you're saying, oh, here is this block on a hill. Where's it going to be in 10 seconds? You did forward dynamics, right? You might not have called it forward dynamics, but that's what you did. Any questions so far? Just tracking? We're just taking this wild, wacky equation, this little manipulator form of Euler-Lagrange equations, and we manipulate it a bit, and we have a nice general form of forward dynamics. Okay? So if you figure out your inertial matrix, which you will be using MATLAB to help you, or you can just get carpal tunnel with your hand, and you can do the same thing with these terms and these terms and these terms, voila, you have a procedure for computing accelerations. It doesn't matter how many Q's you have. But there's another thing you can do. Okay? You could say, hey, what's the opposite of this approach? Instead of saying, I have these forces and torques, what's my acceleration? What if you went the other way? Okay, what could that be useful for? Well, my friends, let's look at this back here. Imagine, you have let's say a robot, and you know the position and speed of all the joints of the robot. Right now, you measure it. You have a sensor that tells you, an encoder that tells you it's at this angle and it's moving this fast because you took the derivative to know it's going so fast, right? You used the symbolic toolbox to come up with the M, C, and G matrices and vectors, okay? Well, you could just plug in your current position and speed and get that number, right? Get that matrix. That's a bunch of numbers. You plug in Q there. We're good. You plug in Q here to get a matrix. What if I said, I want a certain acceleration. I want it to accelerate my arm this way in this direction, or this way in this direction. You know everything on this side. What are you solving for? The forces you're applying with your motors. I could say, I want my robot arm, my whole body of my robot, to move in a certain acceleration. Tell me what torques I need. Now, and give it to the motors. Boom. You can use it for control. This process, where you have some acceleration, and you get out forces and torques, called inverse dynamics. Or ID. it's an oversimplification of what's happening, but let me show you an example. Here's one of our robots in the lab called Digit. My student has the robot standing there. Okay? Right now, it's just standing. Okay? And then it's going to move its body up, okay, a little bit. Let's go before it starts. It's going to start stepping in a moment. But there's a moment where he powers on the robot, but before it starts stepping around. Okay? That's what we're going to focus on here. Okay? Don't worry about the stepping just yet. Here we go. Whoop. Up. Now ignore that it's stepping. That's MPC. That's model predictive control. You're experts on that already. But we're not at the model predictive control stage. We are just doing this here, where he's taking the whole body of that robot and commanding it to accelerate upwards very slowly. That mostly is inverse dynamics. Okay? What is he doing? He has an algorithm, a very fast algorithm, that for whatever position and velocity the robot is currently in, it says, okay, here's M. Here's C and G. And his controller is saying, this is the Q double dot that I want. And what comes out? The torques to the motors. And he gives those to the motors. He applies that torque for like for a millisecond. The robot moves a little bit. And he remeasures, what are my positions? What are my speeds of all my joints? It's everything here. What's my desired acceleration? Is it still the same? Who chooses the desired acceleration? Well, we do. It's what we desire. You gotta know what you want. What comes out? A torque. For all the motors, we tell the motors, apply that torque for another millisecond. What's my position? What's my speed? Rinse and repeat. And that's how the robot take all of its joints. And it's got how many joints? It's got motors. It's got 20 motors. Three-dimensional space. And that's how it operates. Okay? That's how he knows how much torque to apply. And that's really to each of these joints. Because what he could do is he could say, hey, I want each of these joints to go to a particular position. And he could put a proportional derivative controller on each of these joints, move around. But then he has to tune like 20 or 40 gains by hand. My grad student is laughing at this prospect of having to do that. Nightmare. Bad idea. How many gains do we have to tune to do this? Nothing. We just need to know the inertia of our robots, these Coriolis terms, the gravitational terms, and I just showed you how to compute them. Kind of. Not all the way top to bottom, but it's just turning the crank of the math. Okay? Isn't that neat? So you could do inverse dynamics control. Where you could have some Q and Q dot desired, was called Q desired, sorry, Q DES and Q dot DES. Q desired, Q dot desired. Okay? Okay. And it could go into what we call a summing junction, where we measure the actual Q and Q dot. What's the difference between what we want and what we've got? What's the name for that? Error. Okay? And out of that error, we put that error into some kind of controller. Okay? And that controller could give us, hey, these are the Q double dots that we want. And it could be just very simple. The controller could be like, I want my acceleration to be 1 in this direction, you know, whatever that Q double dot is. Okay? And then through inverse dynamics, out comes our torques, which go to our plant. That's just the fancy word for our physical system. Okay? And then you wrap it back around. You sense, you have a feedback controller. Okay. You have inverse dynamics control. What this means is that you have control that accounts for the physical properties of a system and commands accelerations. Now, you could still have a controller, like a PD controller on the accelerations. I could say, hey, I want to be here. I am currently here. And I could say my acceleration that I want is dependent upon how far away I am, right? And you can make that a PD controller if you want. But the key difference is that if instead of holding a pen, I'm holding something bigger, if I update my inertial matrix, which has the weights in here, and like all the other terms, right? And I have the same controller, it'll behave the same. Because inverse dynamics knows I'm holding something heavier, right? So in order to get the accelerations I need, it will know, oh, look at me, I computed these matrices. If I want this desired acceleration, this torque has to be bigger. Because encoded in this mass matrix is going to be the mass. Just update the mass in these matrices, done. Behaves the same. As opposed to if I just put a PD controller saying my torque, or my force that I'm lifting this with is equal to the error, as opposed to the acceleration, the heavier this gets, my controller is going to behave very differently. Okay? You'd have to tune up the gains, right? Isn't that neat? Pretty cool, eh? We will see how far we get on Thursday encoding this up. But one thing I want to do is start having MATLAB generate these matrices for us. Okay? And specifically, my friends, it doesn't really matter for our calculation that these three terms are like separate terms for forward dynamics. They're just everything that isn't an inertia. Okay? So sometimes they call sometimes when you work with simulation packages, you can ask it, hey, friend, what is my inertial matrix? And it'll tell you because you might be trying to do inverse dynamics control. But instead of saying, oh, here's your Coriolis matrix, friend, here's your Coriolis vector, friend, here is your gravitational vector, friend, it'll say, here's everything else together. We call it the bias. Because they know probably what you're trying to do is say, hey, what's multiplied by accelerations and what's everything that's not? So you can solve it. In fact, so there are all kinds of really cool ways to compute these matrices. If you go, but in terms of packages, so software packages. Really good one. It's a simulation package that you can also get all these matrices out of, called MuJoCo. It was developed out of the University of Washington and then was, I believe, consumed by Google And now Google has made it free and open source in Python. Okay? Made by roboticists who needed faster simulation packages. There's a whole lot of things that Majoko does that are way more fancy than just computing these matrices. There's a whole lot, what particularly has to do with, it has really smart ways of handling contact dynamics, so how things make and break contact. But it's a really good simulation package. And I'm teaching advanced dynamics in the fall. My hope is we can teach some Majoko, all right? But my students will use Majoko and they'll create a simulation, and then they will pull out of the simulation at every time step, what's my inertial matrix? And they'll do the math they need to do. Okay? Obviously, you got any kind of symbolic toolbox. MATLAB, which if you don't know, their symbolic toolbox came from Maple, was a different package that they just merged. So if you talk to someone who has been around engineering for a while, they might refer to Maple. Maple's been consumed by MATLAB. Anyone use Mathematica? Anybody? Must be, that's more for hardcore mathematicians. I'm not sure people in the math department use it. They probably do. People who I know who do actual mathematics research, they'll use like Mathematica. Okay. All right. Okay. All right. Where are we at in time? Is this interesting? Show a video of a robot again, make it interesting again. At every point in time, every millisecond, we're recomputing those matrices. Okay. Now, I say we are mostly doing inverse dynamics. We're actually doing kind of a really fancy version of advanced dynamics here. Fancy in a way, okay, we're going to poke it. It's a time-honored tradition. When you're testing a robot, you poke the robot. Okay. So clearly there's higher level elements of control here. Just deciding the accelerations we want of all the joints is actually a little tricky, okay? Even just deciding the acceleration that we want. So we have to add other layers to it. But let's go back to, that's my student Tianzi Wang, by the way. He's now off working at a humanoid robotics company in China, doing awesome things. So let's go back to our non-conservative forces and torques. Okay? Particularly for our pendulum on a cart, right? Okay. Where we had, m of q, q double dot, plus c of q, q dot, that's our Coriolis terms, plus g of q is equal to tau. These are our external forces that we're applying. Okay. We're not going to do the holonomic constraints just yet. We'll try to keep it somewhat simple for this survival guide to Lagrangian mechanics. Get the rapid fire. Do not pass go. Go directly to Lagrangian mechanics. All right. This torque, what is this? We've covered what the m term is. It's this m1 plus m2. It's this 1/2 m2 L cosine of theta and 1/2 m2 L cosine of theta and 1/4 m2 L squared. That's your m. Right now, we don't have any external forces that are non-conservative on the system. Let's add one. Typically, as was in your homework, the pendulum on a cart is controlled with just a force on the cart. That there's not some motor on the pendulum. So it's like a fun game. Like, can you jiggle the cart around to swing up the pendulum and get it to the top? And I gave you all the answer in homework 1, right? I gave you like a trajectory to follow and a feedback controller. I did all that work for you. Okay? So, given the fact that our Q is S of t and theta of t, where that's your angle, and that's S is your position. Tau is going to be a vector of our non-conservative forces, okay? Because f of t is acting on which degree of freedom, friends? S of t. It's going to go in the first column. Okay. And there is no motor or external force explicitly acting directly on theta of t. So that is 0. Okay? So now if you want to apply this force to the pendulum, this is exactly what I gave you the solution to on the homework, right? The force is applied to the first equation, which has to do with S double dot of t, which is the first element of the vector. Okay? All right? Now, my friends, a little conundrum I'll pose to you. Let's say we wanted to do inverse dynamics, where we are trying to solve for tau, what is our forces, what forces do we need to apply to get some acceleration that we want, the inverse dynamics. Okay, we want the block to move and that's at that acceleration, and we want this to move at that acceleration. Well, let's put all this in this equation. It's equal to tau. The first element is going to be the force we have to apply. But look, that second term, if we do all that math, there is no guarantee that this term is going to be 0. In fact, it's very unlikely to be 0. We got a problem. And that problem is called underactuation. We have 2 degrees of freedom, your position and your angle. And how many actuators do we have? 1. 1. Okay? So if you don't have as many actuators as you have degrees of freedom, called underactuated, and you can't apply inverse dynamics arbitrarily. Okay? That is the dime store version of underactuation. There's a beautiful course, I've plugged it many times, by Russ Tedrake at MIT. It's all free and available online about how to handle underactuated systems. But you want to know one of the coolest ways to handle, and most of the best ways to handle underactuated systems for control? Trajectory optimization. We covered it for like 4 weeks. Okay. Our pendulum, because we had limitations on the amount of force we were applying, it was also underactuated. So the way that we would solve it with inverse dynamics would be like, oh, I want to accelerate it up. But then you hit a force limit. You can't apply any more than we asked to do on Thursday. We put a strict force limit on the amount of torque on the pendulum. So inverse dynamics would fail. So instead, we needed trajectory optimization to say, no, swing it. Because it was underactuated. Okay? And write this as underactuated. Fewer actuators than Q's, or DOF, degrees of freedom. So I just want to point out that this inverse dynamics approach won't work well for the pendulum on a cart unless you put a motor on the pendulum as well. Okay? So instead, I'll give you another quick example. We will not even attempt to derive the equations of motion for this today. We're going to leave that to MATLAB, hopefully on Thursday. Call it it's the double pendulum. Christian, what's your obsession with pendulums? I'm sorry, it's just anything attached to anything else is probably a pendulum with pin joints. But it's also a robot arm. It's also a manipulator. It's also some of these 3D printers will have like a Revolut arm. Or these are pin joints, okay, where you have 2 links. They are pin jointed. You have one angle theta 1 of t, and then a second angle, a relative angle theta 2 of t. 2 pendulums attached one to the other, right? And we're going to have a torque at this joint, torque 1, and a motor here, which is a torque at this joint. So it's like my elbow, you know, my shoulder and elbow, right? I got a motor at my shoulder that can move like this, and I can move my elbow. Right? Something I can control, right? Okay. Nifty. So this here is fully actuated. It has 2 degrees of freedom, the 2 angles, and it's got 2 torques. Okay. So we're going to do our Lagrangian dynamics, Lagrangian mechanics. You go through the whole process. You're going to set up your generalized coordinates. You're going to set up your kinetic energy, your potential energy. You're going to compute your Lagrangian L. You're going to do the Euler-Lagrange equations, which also have these added torques to it. We're going to bypass all this with this time-saving arrow. And what you're going to get on the left-hand side is m of q, q double dot, plus a whole bunch of terms, which are the, let's write them out. C of q, q dot, plus g of q. Then on the right-hand side, you have your added torques, tau. Okay? These together, I'm going to combine them. I'm going to call them f of q and q dot. That's my bias. Okay. So it's m of q, q double dot, plus f of q, q dot. Because the differentiation between these things is not useful to us mathematically at the moment. Okay. But then we have our added torques to our system. And this is something I want to just get across as being a nice, as an important detail to not forget about. Okay? There are 2 degrees of freedom. This is going to be here. This is going to be a 2 by 2 matrix. 2 by 2 matrix. Right? It's going to be a 2 by 1. We have 2 degrees of freedom, so that means our tau is going to have to be a 2 by 1. Okay? So, anyone want to guess what I should put for these added torques for each of these entries, the top and the bottom? Anybody? Make a little space in case it's big. What are the torques on my first body? What I hear? Tau 1. Tau 1. What about for our second body? Tau 2. I've tricked you. You're mostly right. You're mostly right. If I have a motor that's mounted here, and it applies a torque to this body, tau 2. What's Newton's third law, friends? Every action is equal and opposite reaction. Where does the reaction torque go? First one, right? If I have a motor that's mounted here, right, and it applies a torque positively in this direction, the thing it's mounted to gets what? Negative. in the other direction. Now, tau 1, that's mounted to the wall, and we just assume the wall ain't moving. The wall is infinite mass, so it doesn't do nothing. Okay? So we get away with that for free. Equal, opposite, reaction. That make sense? So if you think, this is just giving you an example of where you put the torques and forces. What are all the external non-conservative forces on that body? It's tau 1 and negative tau 2. If I added a third pendulum and a theta 3, that would just make this a 3 by 3 matrix. And this would be a 3 by 1 vector. And this would be a 3 by 1 vector of potential torques. And I add an extra torque there, tau 3. If that's a motor that's attached to that link right there, it would be minus tau 3. And that's tau 3. This is all temporary math here. If you didn't have these negative terms here, it would be like there's a magic torque from outside of the pendulum that can say, oh, apply torque. Some people call that the hand of God torque. You know, there's no equal and opposite reaction, right? So that's going to be important to remember when you are adding, forces to your system, including things like friction. Okay? We didn't talk about friction. Let's say that there's friction let's add friction here. Okay. That's going to be an external force with non-conservative. Let's just say it's a linear viscous friction, meaning it's just multiplied by the speed. So it's like a minus c theta 1 dot, right? Okay. Well, that would show up here. This would be minus c theta 1 dot. And if you have a friction force here as well, it's at the joint. It's going to be affecting both bodies. So you have to remember to have equal and opposite forces. So it's going to be minus c theta 2 dot. So it's going to be minus c theta 2 dot. But equal and opposite force on the other link. So plus c theta 2 dot. Right? Okay? All right. That's Lagrangian mechanics. Shockingly fast. Including non-conservative forces. We didn't get the constrained. I showed you a little bit about the constrained thing, but it's actually not too much after the trigonometric constraints. The thing we're going to get to is, well, so we should hopefully do an inverse dynamics next lecture. But one thing I'm hiding from you is that Pienza, when he's making this robot walk around, he also doesn't want to assign all the accelerations for all the joints either. He doesn't want to have to do that. He doesn't care exactly where the knee is. He doesn't care exactly which way the foot is pointing. He doesn't want to have to choose that. He said, you know what I care about? The center of mass of the robot. I want the center of mass to be, you know, 1.5 meters off the ground. I want the foot to be there. I want this to be there. Everything else, I don't really care that much. So he comes up with a controller that says, you know what? There are specific things that I care about called my task. All right? Where's the center of my body? Where is the end of my arms? There are lots of places the end of my arms could be that are still there, and I can still move all the joints around in different ways. Okay? All right. If I have the task of pointing at the end of this pen, I can do it like this, I can do it like this, I can do it like this. That's called inverse kinematics, so that's different. But like, the only thing I cared about is that it's touching the pen. Everything else I don't. okay? So what if I told the controller, this is the only thing I care about? Everything else, figure it out, okay? And this task-based control, where we define this is what we want, how we want our robot to operate in the task. We call this operational space control, okay, or OSC. So that way you don't have to define the acceleration of everybody at every point. You say, this is what I care about. I want to pick up this pen. I want my body to be here. Everything else, I don't care. All right, we're at the end of the class. Thank you so much. Have a good day.